In December 2024, a chip smaller than your thumbnail did something that should not have been possible. It solved a calculation in 5 minutes. The same calculation, run on the fastest supercomputer on Earth, would have taken longer than the age of the universe, 10 septillion years. That's a 1 followed by 25 zeros. And here's the part that gets stranger. 18 months later, a separate team of physicists took a claim almost identical to that one, a claim that a quantum computer had done something no classical machine, no AI, no supercomputer could ever replicate. And they broke it using a laptop. Both of these stories are true. Both of them happened. And by the end of this video, you're going to understand why the honest answer to did quantum computers just beat AI is far more interesting than a simple yes. Let's start with what people actually mean when they say a quantum computer beat artificial intelligence. It's a bit of a shortcut, and it's worth untangling, because the exaggerated version of this story is everywhere online, and the accurate version rarely gets clicks. Every AI system you've ever used, ChatGPT, image generators, self-driving software, runs on classical computers. Massive rooms full of GPUs, crunching ones and zeros. A quantum computer doesn't use ones and zeros. It uses qubits, and a qubit can exist in a blend of both states at once, a property called superposition. When you link many qubits together through something called entanglement, the number of possibilities they can represent explodes exponentially. 10 qubits can represent around 1,000 states at once. 300 qubits can represent more states than there are atoms in the observable universe. That's the theoretical edge quantum computers are supposed to have. The question the entire industry has been fighting over for the last 2 years is simple. Is that edge real, or is it a mirage that clever classical software, including the kind of software that powers modern AI, can always catch up to? That fight came to a head in March of 2025, and this is where our story really begins. A team of researchers, including scientists from D-Wave Systems, published a paper in the journal Science. They had used a quantum computer to simulate something called a quantum spin glass, essentially a disordered system of magnetic particles whose behavior gets almost impossibly tangled as it evolves over time. The team compared their results against every classical simulation method available. Nothing came close, not supercomputers, not machine learning assisted approximation techniques, nothing. They called it a demonstration of beyond classical computation. In plain language, a real-world task that only a quantum computer could do. Headlines ran with it. Funding conversations shifted. It looked like proof that quantum machines had finally crossed a line that AI-powered classical computing could not cross. But not everyone was convinced. And that skepticism is about to completely change how you see this story. At the Flatiron Institute in New York, a physicist named Joseph Tyndall read that March 2025 paper with what he later described as raised eyebrows. Tyndall and his colleagues at the Center for Computational Quantum Physics, and working with researchers at Boston University, spend their careers doing one specific thing: finding clever mathematical shortcuts that let ordinary computers simulate quantum behavior that shouldn't be simulatable. Their tool of choice is something called a tensor network. Think of a tensor network as a highly advanced zip file. A quantum system with hundreds of entangled particles theoretically requires an almost infinite amount of information to describe exactly. But most of that information turns out to be redundant. A tensor network finds the deeply compressed version of that information, the part that actually matters, and throws away the rest without losing accuracy. It's the same basic idea as an MP3 file storing a song in a fraction of the space of the raw audio, keeping what your ears actually notice and discarding what they don't. Tyndall's team pointed this technique at the exact same spin glass problem from the March 2025 paper. And here's where it gets uncomfortable for anyone who wanted a clean, simple headline. Running on a conventional laptop. Not a supercomputer, not a quantum machine, a laptop. Their tensor network calculations matched the theoretical predictions and matched the quantum computer's results. The impossible classical problem turned out to be very possible once someone brought the right math to the table. The result was published in Science and later recovered by outlets including Science Daily in July of 2026, more than a year after the original claim. And whenever we see these kinds of claims, we're always a bit skeptical, Tyndall said. Did you try this? Did you try that? And it's worth understanding why that particular experiment was vulnerable, because it tells you something about the whole field. Not every quantum computer works the same way. Google's Willow chip is what's called a gate-based system. It manipulates qubits with precise, individually controlled operations, similar to how classical logic gates manipulate bits. D-Wave, the company behind that spin glass paper, builds something fundamentally different: quantum annealers. Instead of running step-by-step instructions, an annealer lets a physical quantum system naturally settle into its lowest energy state, the way a marble dropped into a bumpy bowl eventually rolls into the deepest dip. That approach is extremely good at certain optimization and simulation problems, And D-Wave's current flagship, the Advantage 2 system, became generally available in May of 2025 with more than 4,400 qubits, offered both through D-Wave's cloud service and as hardware companies can install on their own premises. But annealers are also, by their nature, harder to verify from the outside, because you can't always inspect every step of how they arrived at an answer. That made the spin glass claim an easier target for a determined classical team to go after with the right mathematical tools. Now, before you assume this means quantum computers are all hype, hold on, because that's not the honest conclusion either. And this is exactly the kind of nuance that most videos on this topic skip entirely. What Tyndall's team did was not artificial intelligence. It wasn't a neural network. It was advanced mathematics and specialized software, engineered by human experts to exploit a very specific weakness in that one experiment's design. It doesn't mean every quantum claim can be undone this way. It means this particular claim could be. Some researchers in the field describe this back and forth as a healthy, ongoing process rather than a scandal. Quantum teams make a claim, classical teams try to break it, and whatever survives that pressure test is the real evidence. Experts genuinely differ on how many of today's beyond classical results will hold up over the next few years. That uncertainty isn't a flaw in the story, it is the story. So if that headline result got walked back, does anything actually still stand? This is where things shift again, and it's worth paying close attention, because this next part is the piece almost nobody explains clearly. Go back to that Google chip from December 2024. It's called Willow, and it's a superconducting processor built at Google's lab in Santa Barbara, carrying 105 qubits. The 5-minute, 10 septillion year comparison came from a benchmark called random circuit sampling, essentially the hardest possible stress test for a quantum chip, deliberately designed so that a classical computer has almost no shortcuts available. Google's own engineers and outside physicists like Winfried Hensinger at the University of Sussex were careful in their language. They called it a demonstration of surpassing classical computing on that specific benchmark, not full quantum supremacy, and not a claim that quantum computers had replaced AI or classical computing in general. Willow's more important achievement, arguably, was something less flashy but more consequential. For the first time, Google showed that as they added more physical qubits to a logical qubit group, the error rate went down instead of up. That's called operating below threshold, and it had been a goal of the entire field since the 1990s. Every previous generation of quantum hardware got noisier as it scaled up. Willow, for the first time, did the opposite. Then, in October of 2025, Google pushed further with an experiment called quantum echoes, again on the Willow chip. The idea works a bit like sonar. You send a carefully structured signal into a system of qubits, disturb one of them slightly, then reverse the entire process, and listen for the echo that comes back. Because of a quantum effect called constructive interference, that echo gets amplified, making the measurement extraordinarily sensitive to subtle details a classical instrument would miss entirely. Google reported the technique running roughly 13,000 times faster than the same physics simulation running on the Frontier supercomputer, using just 65 of Willow's 105 qubits. And critically, this wasn't just an abstract math benchmark. The molecular structure information the experiment produced was cross-checked against nuclear magnetic resonance data, the same kind of real chemistry data researchers use in drug and materials development. That verification step is what separates this from a party trick. It's one of the first cases where a quantum result was checked against a completely independent real-world measurement, and it held up. But here's the honest caveat, because overselling this would be exactly the kind of exaggeration this video is trying to avoid. Quantum echoes solves a narrow, specific class of physics simulation problem. It is not a general-purpose replacement for the AI systems training language models or generating images. It's closer to a specialized instrument than a competitor to ChatGPT. IBM, Google's biggest rival in this space, has set its own target of demonstrating quantum advantage on an industrially relevant problem sometime in 2026. Not a cherry-picked physics benchmark, but something with actual economic value attached to it. Whether that target gets hit on schedule is genuinely unresolved, and IBM itself has treated quantum timelines cautiously after years of the industry overpromising. So where does artificial intelligence actually fit into all of this? Because so far, this has mostly been quantum versus classical computing, not quantum versus AI specifically. This next part is the piece that ties the whole story together, and it's not the piece most headlines lead with. The real relationship emerging between quantum computing and AI in 2025 and 2026 isn't a boxing match. It's closer to a partnership, and the clearest evidence comes from pharmaceutical research. In June of 2025, a collaboration between IonQ, AstraZeneca, Amazon Web Services, and NVIDIA tackled something called the Suzuki-Miyaura reaction, a chemical process that's fundamental to how many small molecule drugs are synthesized. Modeling that reaction accurately with pure classical computing is brutally expensive, because you need to track the quantum level behavior of electrons in ways that grow more complicated the more precisely you try to model them. The team built a hybrid system. IonQ's Forte quantum processor handled the parts of the calculation that genuinely benefit from quantum mechanics, while NVIDIA's H200 GPUs, the same kind of chips that power today's largest AI models, handled everything else through a platform called Q2Q, running on Amazon's cloud infrastructure. The combined system delivered more than a 20-fold speedup over previous methods, cutting a simulation that used to take months down to a matter of days. IonQ's CEO at the time, Niccolo de Masi, called it a meaningful step toward practical quantum computing applications in chemistry. And IonQ isn't operating alone in that race to make quantum computing commercially useful. Quantinuum, formed from the merger of Honeywell's Quantum Division and Cambridge Quantum, launched a system called Helios in November of 2025, which the company describes as the most accurate commercial quantum computer available. According to reporting on the launch, organizations including JP Morgan Chase, SoftBank, Amgen, and BMW are already running research on the system. None of these companies are claiming quantum computers have replaced their existing AI and classical infrastructure. They're testing where a quantum processor can shave time or cost off a specific, narrow piece of a much larger workflow, which is a far less flashy story than quantum beats AI, but it's the one actually backed by paying customers. Notice what actually happened there. Quantum computing didn't replace AI-powered classical systems. It worked alongside them, each one doing the part of the job it's naturally suited for. That pattern shows up again and again across the industry right now. In finance, where firms are testing quantum-assisted portfolio optimization; in logistics, where companies are experimenting with quantum methods for scheduling and routing problems that get exponentially harder as they grow; and in materials science, where researchers are trying to design better batteries and catalysts. Forbes reported in December 2025 that the expected shape of 2026 is businesses building hybrid workflows, where quantum processors handle the specific optimization and simulation tasks they're good at, while classical supercomputers and AI systems manage everything else. That's a very different picture than quantum beats AI. It's closer to quantum joins the team. There's one more piece of this puzzle worth understanding, because it explains why so much confident-sounding language about quantum machine learning deserves a skeptical eye. Researchers have spent years trying to build quantum versions of machine learning algorithms directly. Quantum neural networks, quantum kernel methods, systems that would, in theory, learn patterns using qubits instead of classical processors. The honest state of that specific subfield, as of 2026, is that a proven, practical, real-world advantage still hasn't arrived. There's a well-documented pattern in this research called dequantization, where classical scientists repeatedly find clever ways to reproduce the performance of proposed quantum learning algorithms using nothing but ordinary computers, echoing exactly what happened with that spin glass paper. That said, it's not all discouraging. Earlier this year, researchers demonstrated a mathematically airtight case where a quantum learning method could classify a very specially constructed dataset with high accuracy, while proving that no classical algorithm could do meaningfully better than random guessing on that same data. The catch, and it's a significant one, is that the dataset was deliberately engineered around a hard cryptographic problem specifically to favor quantum methods, and the experiment required a level of fault-tolerant hardware that doesn't fully exist yet outside the lab. What it proves is that a genuine quantum learning advantage is possible in principle. It does not prove that advantage is sitting inside your everyday spreadsheet or your company's dataset waiting to be unlocked. It helps to think about the difference between these two technologies using a simple comparison. Imagine you're trying to find the fastest route through a city with a million possible paths. A classical computer, even one supercharged with AI, has to check those paths largely one at a time, or in large but still limited batches, getting faster through clever shortcuts and pattern recognition. A quantum computer, in theory, can explore a huge number of those paths simultaneously because of superposition, then use interference, the same wave-like effect behind the quantum echoes experiment, to cancel out the bad routes and reinforce the good ones, leaving the best answer standing at the end. That's the theoretical promise. The practical reality, as this video has shown, is that classical computers keep finding better and better shortcuts of their own. And every time quantum researchers claim a task classical methods can't touch, there's a real chance a physicist with the right compression trick is already looking for a way to prove them wrong. That ongoing contest is not a weakness in the science. It's exactly how good science is supposed to work. So let's pull all of this together, because the picture that emerges is more layered than a single dramatic headline can hold. Quantum computers have, in specific and carefully verified circumstances, done things that no classical computer, including classical computers running the best AI-assisted techniques available, could do at the time. Google's quantum echoes result, cross-checked against real chemical measurements, is probably the strongest single example available right now. At the same time, other headline claims of beyond classical performance, including that widely reported March 2025 spin glass result, have already been challenged by classical researchers armed with better math, not better AI, and the door on those specific claims is not fully closed. Meanwhile, the place where quantum computing is delivering the most reliable, repeatable real-world value right now isn't in some head-to-head contest with artificial intelligence at all. It's in partnership with it. Quantum processors and AI-optimized GPUs working the same problem from two different angles, the way IonQ, AstraZeneca, AWS, and NVIDIA did with drug simulation. If you've made it this far, you now understand this topic more accurately than most of the videos and articles circulating about it. And if that kind of grounded, no-hype breakdown is useful to you, subscribing helps this channel keep digging into stories like this one before they get flattened into a clickbait headline. What's genuinely exciting here isn't a single chip or a single headline number, it's the shape of the trend underneath all of it. Every year, since Google's original 2019 supremacy claim, the classical response has gotten faster and smarter. And every year, quantum hardware has pushed the target further out of reach again. Sycamore's 53 qubits became Willow's 105. 10,000 years became 10 septillion. A narrow lab curiosity became a verified chemistry measurement. Nobody serious in this field is promising you a quantum laptop on your desk next year. IBM's own public target for an industrially useful quantum advantage is sometime in 2026, and even that comes with the caveat, from IBM itself, that the industry has a long history of moving those goalposts. What we do know, with real evidence behind it rather than speculation, is that the story of quantum computers proving something classical machines and AI systems genuinely cannot do has already happened at least once under scrutiny with independent verification. Whether that becomes a rare exception or the first of many will likely be decided over the next 2 or 3 years, not by another dramatic announcement, but by exactly the kind of quiet, skeptical laptop-wielding scientists who keep checking the math. That tension between the announcement and the verification, between the headline and the follow-up paper nobody reads, is the real story of quantum computing right now. Not a finish line that's already been crossed, but a genuine, still unfolding contest between two of the most powerful ideas in modern science, being fought out in real time in published journals by people willing to say, "I'm not sure yet," when that's the honest answer. If this breakdown helped you actually understand where things stand instead of just what the headlines want you to feel, give it a like so more people see the accurate version of this story, and I'll see you in the next one.